Arjun, I love how versatile large language models are, but I often catch them making things up or just being flat out wrong about recent events. It's frustrating.
That's a common experience, Maya. LLMs are powerful, but they have inherent limitations due to their training data. This leads to what's often called hallucination.
Hallucination? It sounds like a bug, but is it actually a feature of how they work?
Think of it this way. LLMs are brilliant students who studied intensely for years, but then stopped reading the news. Their knowledge is frozen at their graduation date. This analogy holds for their fixed knowledge base. But unlike a student who can actively seek out new information, a traditionally trained LLM cannot update itself after its training cutoff.
So they're like brilliant experts who are just stuck in the past? That makes sense for current events. But what about just fabricating facts?
Exactly. This problem is explicitly named here as knowledge cutoffs. Their training data is frozen at a specific point in time, creating a gap for recent developments.
That's why they can't tell me about last week's basketball game. Their world knowledge just hasn't been updated since their training. I see the cutoff, but why do they then confidently provide outdated or completely fabricated information? Why not just say, I don't know?
Their goal is to generate plausible text based on patterns from their vast training data. They don't have a mechanism to distinguish what they know from what they don't know. The core issue is that output generation is probabilistic. They assign probabilities to all possible continuations, even incorrect ones, and aim for natural-sounding responses.
So if the most probable continuation is a made-up fact that sounds convincing, they'll choose it without hesitation? That's unsettling.
This challenge led to a pivotal idea presented in this paper, Retrieval-Augmented Generation for Knowledge-Intensive NLP Tasks. RAG was designed to address these very limitations.
Retrieval-Augmented Generation. So it's about adding a retrieval step to the generation process?
Precisely. Lewis et al. Introduced models which combine pre-trained parametric and non-parametric memory for language generation. This is the core architectural shift. Practically, this means the LLM's internal representation, parametric, is now explicitly influenced by external data, non-parametric, before it generates its response. The external data provides fresh, ground truth input to the LLM's existing learned patterns.
Parametric and non-parametric memory? What does that mean in practical terms for an LLM?
Parametric memory is the knowledge stored within the LLM's vast number of weights and biases during training. Non-parametric memory is external, a separate database of facts.
So the LLM itself is the parametric part, and the non-parametric part is like an external, up-to-date reference library? This analogy is good for understanding the separation, but it's important to remember that unlike a human library user, the LLM doesn't browse the library directly. It receives specific, pre-selected excerpts.
That's a good analogy, extending the idea of access. However, the student, LLM, still processes the information quite differently than a human would, often by concatenating retrieved text directly into its input, rather than synthesizing it with complex reasoning.
The student still needs to read the books, but at least they're not guessing anymore. This sounds like a fundamental improvement.
It is. This separation of knowledge is key. Let's dig into how RAG actually achieves this, step by step, and builds a truly dynamic system.
I'm ready to see how this smart library works for the LLM.
Let's picture the RAG process as a skilled research assistant. When you ask a question, this assistant doesn't try to answer from memory alone. This analogy helps visualize the steps, But unlike a human, the RAG system performs these steps computationally, without human understanding or subjective judgment.
Instead, they go find the information first, like a human researcher, which is definitely what I want an LLM to be more like.
The first step is ingestion. Authoritative data, like company proprietary data, is loaded into a data source. This is about preparing our external knowledge base, getting all the relevant information ready.
So, before any questions are asked, we feed the system all the up-to-date relevant documents it might need.
Exactly. This involves 3 sub-steps: chunk the data, create vector embeddings, load data into a vector database. To create vector embeddings, a specialized embedding model processes each text chunk and transforms it into a high-dimensional vector, a list of numbers, that numerically captures its semantic meaning. Chunks with similar meanings will have vectors that are numerically close to each other in this space, making the data semantically searchable.
Splitting documents into smaller pieces, turning them into numerical representations, and storing them for quick access. This reminds me of vector embeddings we've discussed before.
It should. The embedding model is a special type of LLM that converts the data chunk into a vector embedding. This is the same principle of semantic similarity we saw with hashtag TCM153005.
So the vector database stores these embeddings, allowing it to find semantically similar chunks, not just keyword matches. That's clever.
Once ingested, the next step is retrieval. Relevant data is retrieved from an external data source based on a user query. This is where the research assistant gets to work. When a user asks a question, that query is first converted into its own vector embedding. Then, the system compares this query embedding to all the stored document chunk embeddings in the vector database, typically using a similarity metric like cosine similarity to find the most semantically relevant chunks.
The user asks a question, and the system looks for the most relevant chunks in its vector database.
Imagine asking an LLM, what are the health benefits of green tea according to the latest research? The retriever searches the embedded research papers for relevant sections. It doesn't just guess, it finds actual passages from credible sources that specifically address green tea benefits. That's powerful.
Next comes augmentation. The retrieved data and the user query are combined into a prompt. This is a crucial step where the retrieved relevant text chunks are typically concatenated directly into the prompt alongside the original user query, often following a specific template like, here is some context, retrieved context. Based on this context, answer the following question, user query.
So it's not just the question anymore, it's the question plus all the relevant information concatenated into one super prompt.
Exactly. The LLM doesn't perform the retrieval itself, it acts on the augmented prompt. This is where basic RAG differs from approaches like web search in real time.
That's an important distinction. The LLM isn't browsing, it's reading the context you gave it.
Finally, we have generation. The model generates output from the augmented prompt using the context. The LLM now has the specific information it needs.
And because it has that specific context, it's far less likely to hallucinate or provide outdated information. It's grounded.
Precisely. This four-step pipeline is the foundation, and it brings significant advantages. One major benefit is access to real-time data and proprietary or domain-specific data. This means LLMs can now use the latest news or even internal company documents.
So, no more knowledge cutoffs, and it can be used for highly specialized or confidential information.
Exactly. Another critical aspect is that RAG builds trust. Because the output is grounded in retrieved documents, it's often possible to provide citations or references to the original sources.
That's huge. Being able to verify the information directly addresses the loses trust pitfall we mentioned earlier.
Indeed. We also gain more control over the LLM's behavior, as we can dictate which sources it draws from, enforce guardrails, and trace its responses back to specific documents.
It sounds like we're not just making LLMs smarter, but also more reliable and accountable. What about the cost?
And yes, it's often cost-effective compared to alternatives like training or retraining your own model, fine-tuning, or stuffing the context window. Updating an external knowledge base is far cheaper than constantly retraining massive LLMs.
So, RAG is a game changer for practicality and performance. But what were the original creators thinking, and are there still limitations?
While incredibly powerful, even the basic RAG pipeline, as we've just described it, has evolved. The original paper explored more sophisticated retrieval, and the field has since advanced even further to address new challenges. Let's delve into those deeper architectural insights and how they laid the groundwork for even more advanced RAG approaches.
Intriguing. So even RAG has evolved beyond its initial form. Tell me more.
We've previously explored how large pre-trained language models have been shown to store factual knowledge in their parameters in cases like TCM 15305 on transformers.
Yes, their weights become a vast, implicit knowledge base, but one that's fixed and hard to update or verify.
The Lewis et al. Paper clarifies this. RAG models, where the parametric memory is a pre-trained sequence-to-sequence model, and the non-parametric memory is a dense vector index of Wikipedia. This explicit separation and integration was a core innovation.
So the LLM itself, like a transformer-based sequence-to-sequence model, is the parametric part. And a vast searchable index, Wikipedia here, is the non-parametric part.
That's right. Crucially, this non-parametric memory is accessed with a pre-trained neural retriever. This retriever isn't just a simple search algorithm. It's another neural network, often fine-tuned specifically to understand the semantic meaning of queries and passages, ensuring it pulls the most relevant context, not just keywords.
The retriever isn't just a keyword search. It's a sophisticated component that understands the query's meaning to find the best context.
Correct. This isn't just adding a database. It's adding an intelligent component that dynamically selects the most relevant information for the LLM to consume. The quality of retrieval directly impacts the quality of generation.
So the intelligence of retrieval is as important as the size of the external knowledge base itself.
The original RAG paper even explored advanced forms beyond just a single set of retrieved documents for an entire response. They compared RAG that conditions on fixed passages versus one that can use different passages per token. Wait, different passages per token? Does that mean the retriever can pull new information as the LLM is generating each word? Exactly. It means the model could dynamically reevaluate and fetch new context for each part of its generated response, much like a human writer might consult different sources mid-sentence as they craft their argument. This allows for incredibly fine-grained grounding and potentially much higher accuracy.
That's mind-blowing. It's like the LLM has a tiny research assistant on constant standby, fetching exactly what it needs exactly when it needs it. But even this sounds like it still just accepts whatever is retrieved.
You've hit on a crucial point. The early RAG models, even with dynamic retrieval, largely acted as passive consumers of retrieved information. This observation led to the next wave of innovation, models that could actively critique and reflect on the information they retrieved and generated. Let's explore how they added this wisdom layer.
So from just having a memory to having a mind to use that memory intelligently, I'm intrigued.
As this source puts it, the traditional RAG approach is simple, often with a vector database and a one-shot prompt with context sent to the model to generate output. This means the LLM might just take the first few retrieved passages, even if they aren't perfectly relevant or are contradictory. It doesn't question the source or the content.
So the LLM just gets a big chunk of text and has to make sense of it, even if some parts aren't perfectly relevant or are contradictory. It doesn't question the source or the content.
Precisely. It lacks the internal self-correction mechanism a human would employ. This led to advanced RAG frameworks like self-RAG, described in our mental model. Self-RAG introduces the ability to internally evaluate the accuracy and relevance of the retrieved context.
An internal critic. So the LLM itself judges if the retrieved information is good enough instead of just blindly accepting it?
That's the core idea. Self-RAG empowers the LLM to apply reasoning to validate retrieved information, to trust or discard it. This means it can identify irrelevant or even conflicting information from its retrieved passages and critically decide if it should be used.
And if it discards it, does it then try to retrieve something else adaptively?
Exactly. This adaptive retrieval is a hallmark of self-RAG. It doesn't just retrieve once, it can iteratively refine its retrieval strategy based on internal reflection signals, prompting itself to get better information if the first pass isn't sufficient. It's like having a metacognition layer for retrieval.
So it's not just using external memory, but actively thinking about how it's using it. This sounds like a huge leap towards more reliable and intelligent systems, reducing hallucinations even further.
It truly is. From simply gaining access to external knowledge, RAG has evolved to systems like self-RAG, where the LLM can intelligently interact with that knowledge, critically assess it, and even decide when and how to retrieve more. It transforms the LLM from a passive reader of context into an active researcher and self-corrector, pushing the boundaries of what these models can achieve.
So RAG is about giving LLMs memory, and advanced RAG is about giving them the wisdom and critical thinking to use that memory effectively. This completely redefines their capabilities for factual, grounded, and dynamic knowledge processing.